This conference will now be recorded.
Hello students, we had been discussing diffraction of light for last 2 lectures. So today what I am going to do is I am discussing numerical problems as well as few analytical questions on this diffraction of light. So here by discussing these questions we will try to clear our understanding about diffraction of light, and at the last we will have some numerical problems from NEET papers, and in the next class we will take up various problems from iitjee papers, previous year's paper. So let us start today's session. So this question says, which of the following ray gives more distinct diffraction? So you look here, the rays are given here: X-ray, radio waves, gamma ray, and light. So we have these rays. So out of these 4 rays, which one will give more distinct diffraction? Okay, so you know we have condition for diffraction, as I was showing you in the very first class, that light gets bent, that's very fine, but you know when your slit width is going to be narrower, okay, narrower, we see more spreading of light. What was the conclusion from this? Conclusion was that if the opening or the aperture is nearly equal to or comparable to the width of the slit, okay, width of the slit, if the wavelength of the light is, or whatever wave it is, whether it is sound wave, light wave, or maybe other waves, so this wavelength has to be comparable to the width of the slit or the aperture. This is the one point. So this is actually condition. See, slightly less than also is fine, okay, slightly less than sorry, this yeah, so wavelength has to be equal or slightly less than d, then the diffraction will be actually seen. Now one more point is that if you look this width of central maxima, or any maxima, see I have pattern like this, isn't it? So I have central maxima, then we have other minima, right, like this on either side. I'm sorry, these are not of equal intensity, like that, okay. So this will have on either side, also will have similar pattern like this, okay. So this is the central maxima. So we have seen the width, fringe width beta of the central maxima to be equal to 2 d lambda by a, okay. So this is width, this is my lambda, wavelength. So you know somehow it is actually directly proportional to lambda, okay. So you look here, if we want to have a distinct or clear width, of this, and in fact not only for the central, for the other minima also. This is for central one, right? So for the secondary maxima also, you look, the width will be directly proportional to lambda, isn't it? So if lambda is very, very less, then width will be very less. If lambda is more, width will be more. So it is very much understandable that if the wavelength is, see, I have 4 rays, right? So I'll just say gamma ray here. Then see, if I draw the spectrum, if you remember the spectrum, see, wavelength is actually increasing in this way. So first gamma ray, okay, then comes X-ray, and then comes visible light, okay, light or visible light, then radio waves, okay. Radio waves has actually greater wavelength than all others, okay. So gamma has larger energy but lesser wavelength, least wavelength among these 4. So you can understand that the fringe pattern or diffraction fringe will be actually very, very distinct with this, okay, with the radio waves, okay, with the radio waves. So among this, see, X-ray diffraction generally we do for crystals, okay. Crystals are opening some angstrom order, right? Angstrom order. So we go with this because X-ray wavelength can vary from 0.1 angstrom to 100 angstrom, right? So we go for this. Actually, I haven't had diffraction with gamma in practical use. Okay, light diffraction we see in the laboratory. So X-ray diffraction generally used for crystallography, okay, for crystallography. All right, but anyway, in normal case, if you take these things, these 4 lights, so radio waves will be giving you more distinct diffraction pattern because it has greatest wavelength among all these, okay. So what is the answer here? The answer is radio waves. Now go to the second question. What happens when the width of the slit aperture is increased in an experiment of single slit diffraction pattern? Spread, see the options, let us see the options. We know single slit experiment we have already discussed yesterday. We have, say, whenever required, we can recall our formula, like the condition for, see, path difference for dark one will be delta is equal to n lambda, okay. Path difference has to be this. For bright one has to be 2n plus 1 lambda. So this is for dark pins to occur. This is for bright or secondary maxima, we can say. This is for secondary minima, okay, secondary minima or dark, I'm saying here. So this will, there will be lambda by 2 here, okay. And if we require furthermore, like say, if we require the angular width of this dark or bright, they both have angular width same width, that is, this one, it is called a lambda by a. And for the angular width for the central one will be 2 theta for central one, 2 lambda by a, 2 theta for central one, okay. Central maxima, this is angular width, I'm writing aw, okay, aw for central maxima. central maxima. Okay, this is about a few informations. We have much more informations. Let me see which parameter they are going to say in the options. Okay, see what happens when the width of the slit. So width of the slits, we have to recall formula for these things with the width of the slits. Slit aperture here actually this this A is the slit width here, slit width. So slit width is increased, then what will happen? Spread of diffraction region, will be decreased. Mid band becomes narrow. Let us see what happens if this A is increased. See here we can understand from these expressions that the angular width of the fringe width or fringes like maxima or minima or central maxima, they are actually, see this width are actually depending on our angular spread is inversely proportional to the slit width, inversely proportional to the slit width. So I can say spread will be inversely proportional to 1 by slit width. So spread will be definitely decreasing if the slit width is increasing, right? And at the same time, mid band, if the spread is decreasing, say suppose you have, I'm drawing a smaller one like this. Okay, so here also like this. Now if this thing is spread, is this whole pattern or whole diffraction pattern is actually the spread of whole diffraction pattern is less, then obviously this will be narrower like this, right? Narrower here like this, isn't it? So it is becoming narrower, that is obvious. So this option might be correct. Let us see the other options. Spread of diffraction region is decreased. This is alone, this is fine. Spread of diffraction region is increased, this is not correct anyway. None of the above. I think you can go for the more appropriate answer for this, but this is also correct. Okay, spread of diffraction region will be decreased. That is also correct. Okay, so most appropriate answer will be this one. The spread of the diffraction region will be decreased and mid band becomes narrow. Okay, all right, so let's go to the next problem. Next question. In the diffraction pattern of a single slit aperture, that means single slit Fraunhofer diffraction, with the width of the central fringe compared to the width of the central maxima, secondary maxima or minima. That means what will be the fringe width? We have discussed yesterday already, but still I'll just discuss once again. If you have not seen my previous video, then please go and see that. Otherwise also you will be benefited from here itself. See, we have we have central maxima and minima, width of the central maxima and minima. Before that, let me tell you, if suppose this is the intensity pattern, the central maxima, then comes secondary maxima, then other maxima, minima, etc. Like this. So I'm just drawing one side alone just to save my time. So you know this spread, okay, this spread linear. See, you have to see the width, right? Width of the secondary maxima and secondary minima, and width of the central maximum and central minima. For that, you know what you have to do? You need to find out the position of the linear position. Okay, linear position from the central. Okay, this we had taken as y. Okay, y. So linear distance from the central maxima. So this yn for the minima or dark one is n d lambda by a. Okay, this is for the dark one. Now look, the central maxima, let me just find out. Okay, for bright also, see bright one, this is for dark one, position of the dark fringes from the central one. Okay, and position of the bright fringes from center. Okay, central one is given by 2n plus 1. Just we have to multiply d, that's all. 2n plus 1 d lambda by a. Okay, this is with, this is actually the position. So look, if I want to have the width of the central maxima, I can get easily by see, if I know the position of these two, see this position will be d lambda by a, and this side it will be minus d lambda by a, right? If we just take the difference of these two, then what will be that? That will be actually 2d lambda by a, right? Now what is the width of this secondary maxima or minima? First of all, I'll tell you the width of the secondary maxima and minima will be obtained from here. If I see, if I want to get beta for dark, see, I can just make like, say, n plus 1 minus of yn. Okay, if you do that, you'll be seeing that this will be lambda d by a. Okay, lambda d by a. And for bright one also, if you just do this thing, yn minus 1, you will look that you will get this also d lambda by a. So this thing you will get. So d lambda by a is the width of the bright one or dark one, and 2d lambda, because you can see here, this is the position of d lambda by a. This is d lambda by a. This is the linear position, linear distance from the central one. If I say this is o to this minima, first minima p1. Okay, so this distance is d lambda by a. This is minus d lambda by a. If you take the difference, you will get 2d lambda by a. So it is actually, see, we are comparing the width of central maxima or central fringe compared to the width of the secondary maxima or minima. So any of secondary maxima and minima, they are of equal width, and see, this will be 2 times of that of, so central maxima. Okay, width of the central maxima will be 2 times of that of the fringes of secondary maxima or minima. Others see 4 times. No, it is not 4 times, not half, even not same. Okay, it is not same. It can be seen from the diffraction pattern itself. Okay, so it is actually 2 times. All right, so let us go to the next question. In a single slit diffraction pattern, if the light source is used less wavelength than previous one, then width of the central fringe. So width of the central fringe is, we have already discussed, this is d lambda by a with 2 multiplied here. This is width of the central maxima or central fringe. See, suppose first you take some wavelength lambda 1 and do the experiment, you get this one. Okay, you just take some other lambda 2 which is less. Lambda 2 is less than lambda 1. So now, see, beta central will be 2d lambda 2 by a. So since beta is actually directly proportional to lambda, if the wavelength is less, then obviously the width of the central fringe is going to be decreased. Okay, it is going to be decreased. All right, let us go to the next problem. In Fraunhofer diffraction by slit, if slit width is a, wavelength lambda, focal length of the lens is f, linear width of the central maxima. So here, if you remember, I have slit in front of a diffraction. What we do, we use two lenses actually. So this is L1. So just before the slit, L1, and the source here, point source, some source which is monochromatic source, which is kept just at the focal length of this L1. Okay, so that we get parallel rays from here after refraction. Okay, parallel rays. Now see, here also we use another lens. We use another lens which has focal length, if I have kept it at the middle of this screen and slit. If I keep this in the middle of slit and screen, this is length L2. Okay, so generally light will be after the diffraction, the rays will be parallel, parallel to each other, but we want to make them meet on the screen. That's why the screen is kept exactly at the focus of this L2 lens. Okay, all right, so this focal length, so this is the focal length we can just consider. Okay, so the question is, in a Fraunhofer diffraction by a slit, if the slit width is a, wavelength lambda, focal length of lens is f, linear width of the central maxima. So what is the linear width of the central maxima? Okay, so here, see, we know we have to find out the linear width of the central maxima, right? So linear width. Okay, so the distance of first dark band and the next bright band from the axis okay, so here the answer is actually lambda f by a. Okay, so lambda f lambda by a. So this is the answer actually here. Okay, so this is the width of the central maxima. Width of the central maxima. Okay, so I think we'll come back to this question once again. Let us now go with this option. So this question is saying that a light source of 5000 angstrom wavelength produces a single slit diffraction pattern. Okay, so the first minima in the diffraction pattern is at a distance 5 millimeter from the central maxima. Okay, the distance between screen and the slit is 2 meter. That means d is given 2 meter. See, this is first minima. The first minima in diffraction pattern is seen at okay from so y1 is given as 5 millimeter. Y1 is given as 5 millimeter. Okay, so we know minima will occur yn is equal to n d lambda by a. Okay, so n is see this is n is 1 here in this case. So from here we will get the answer. Okay, so you have to find out what is the width of the slit. That means a you have to find out. So y1 will be given as by a. Okay, so this this is given here 5 millimeter and d is given as 2 meter. So I can write this as okay, so 2 meter. Here it is lambda is given as angstrom, so 5000 angstrom. We can actually bring all of them in same unit. Okay, so let us write this as 5 into 10 to the power minus 3 meter. Say angstrom lambda is given as 5000 angstrom. This we can write 10 to the power minus 10 meter. Okay, so you get here, if we put the values here, so a is equal to y1 into d lambda, sorry, y1 is given, so a will be written as d lambda by y1. D is 2 meter, lambda is 5000 into 10 to the power minus 10 divided by y1. Y1 is 5 millimeter, 10 to the power minus 3. Okay, so this goes like this 336, so it will be 10 to the power minus 4. Okay, so 10 to the power minus 4 meter. Okay, because this will actually cancel 5000, it will be here, so this comes 6. Okay, so it is like that. Okay, so it will be in millimeter, it will be 0.2 millimeter. Okay, so this is the answer. Let us go to the next question. A plane wavefront of wavelength given here is incident on a slit of with this. So let us write this in millimeter. We have to find out. So let us make this into 10 to the power minus 10 meter. Slit width millimeter it is given, so 10 to the power minus 3 meter. Screen is at 2 meter away. Width of the central maxima. We have to find out the width of the central maxima. So we know this will be 2d lambda by a, right? This is the width of the central maxima. Okay, so 2 into d. D is, sorry, this is meter. D is 2 meter. Lambda is 6,000 into the minus 10 meter. 2d lambda by a. A is given as 0.2. 0.2 into 10 to the power minus 3. That means, you know, this is 2 into 10 to the power minus 4. What we get then? See, this goes with this. So this will be 12. So this 4 and this 3 will be 7. So it will be into 10 to the power minus 3 meter. Okay, so it will be 12 millimeter. Okay. All right. So let us go with NEET questions. Okay, questions from NEET UG paper 2013. A parallel beam of fast moving electrons is incident normally on a narrow slit. A fluorescent screen is placed at a large distance from the slit. That means form of a diffraction is happening. The speed of the electron is increased. Which of the following statement is correct? Speed of the electron. See, when we have electrons, you know, so this wavelength of the electron is actually de Broglie wavelength. Okay, de Broglie wavelength, that means matter wave. It is given by h by p according to the de Broglie's hypothesis, or h by mv. Now look, if this increases, if the speed of the electron increases, then what happens? Lambda decreases. Okay, lambda decreases. What you have to find out? So look, these are the things we can get from the question itself. Now let us see the options. The option says the angular width of the central maxima will be unaffected, which is not true, because the beta central is 2d lambda by a. So it is actually depending on lambda. So it is unaffected. This is not true. Diffraction pattern is not observed on the screen in the case of electron. Now this is not true, because diffraction of electron diffraction is there. Okay, there are experiments you can see in your higher standard electron diffraction. Angular width of the central maxima of diffraction pattern will increase. This is also not true. The angular width of the central maxima will decrease. Yes, this is true. Okay, now go to the next question. This says diffraction in a diffraction pattern due to single slit of width a. First minima is observed at an angle this. First minima a sin theta is equal to lambda. This is the condition for first minima. First minima, okay, occurs at this condition, right? This we have already discussed, and you might be also knowing. When the light wavelength is given, this 5000 angstrom is incident on the slit. The first secondary maximum is observed at an angle. See, secondary maxima. Secondary maxima observed at an angle. You have to find out what is the condition for that. You know, right? You know the condition. What is the path difference? Here path difference is anyway a sine theta. This has to be 2n plus 1 lambda by 2. So this is the condition for nth one. For the first secondary maxima, it will be n is equal to 1 for first one. So n is equal to 1. A sine theta is equal to, so this is n is equal to 1 means 3 by 2 into lambda. This is the condition for observing first secondary maxima, for first secondary maxima. Okay. All right. So from here you have to find out what is the angle. So this theta you have to find out. Okay. So theta, let us write for sine theta is equal to 2 by 3 here a. Okay. This is lambda. I think a. Okay, so a we have to find out from here because it is given first minimum is occurring at 30 degree. Okay, so a will be lambda by sine 30. Sine 30 means half. Sine 30 half. So 2 goes there. So 2 lambda. A is equal to 2 lambda. Okay, a is equal to 2 lambda. So here I can put the value. Okay, let me write first once. So sine theta. Okay, let me just erase this part. Otherwise, you will be confused. So this was required to find out what is A. Okay, so first line. Okay, so in a diffraction pattern, due to a single slit of which A, the first minima is observed at an angle 30. So this is required for finding out the A. So we have found out A. Now let us put this lambda. Okay, 3 by 2 A into lambda. So what is A? This is lambda. So A is actually 2 lambda. We have seen that. Right here 2 lambda. Lambda goes. So this will be 3 by 4. Okay. So obviously you can see that this option will be correct. Okay. So theta will be sine inverse 3 by 4. All right. So this is the answer. Now the next question. This is from NEET paper 2019. Angular width of the central maxima in front of a diffraction is okay. Diffraction for the lambda is given, so 6000. So these are similar type of question. This is 10 meter if I require. Okay, when the same slit is illuminated by another monochromatic light, the angular width decreases by. Okay, good. So decreases by 30%. So what is the wavelength of the light used? See, first one wavelength 6000 angstrom was used. So okay, so the central width of the central maxima was found to be theta 0. Okay, now when the same slit is used but another wavelength, another monochromatic light has been used. So let me just give the name this as 6000 angstrom anyway. Let me do one thing here. Lambda 1 is 6000 angstrom. Lambda 2 we have to find out. So what is said if this beta 1 is the corresponding to lambda 1 and beta 2 corresponding to lambda 2. Let me say it is decreases by 30% means what, you know, this if I take the mod of that beta 2 minus beta 1, or let me decrease means I can write beta 1 minus beta 1 minus beta 2 divided by beta 1 into 100. This is equal to 30. This is equal to 30. Okay, so this is what is given. Okay, so what is beta for central maxima? So this is, you know, d 2 d lambda by a. Okay, let us do one thing. We'll just, if we put this here, what we have, beta means 2d by a. See, 2d by a, this I will take common. 2d by a, I'll take common because same screen, same slit. So 2d, this lambda 1 here, this will be lambda 1 minus lambda 2 divided by lambda 1 here. Okay, so here also the same parameters will come. So this will be going away from both sides. Okay, so this will be 30 by 100 here. So from here, look, we have to find out lambda 2. So I'll just take this. See, lambda 1 minus lambda 2 is equal to 3 by 10 lambda 1. Okay, so lambda 2 will be what? Lambda 2 will be lambda 1 minus 3 by this, right? So this will give you lambda 1. So 7 by 10 into lambda 1. Okay, 7 by 10 into lambda 1. Okay, so let us see what is that. So lambda 2 is going to be 7 by 10 into lambda 1 is given as 6000 angstrom. So this will be like this. So this is this much angstrom. So this is the answer. Okay, I hope guys you have understood. So this is how you can do the calculation. Now I think this is the last one. Yes, last question, and I will end this session here itself. So angular root of the central maxima of a diffraction pattern on a single slit depends on, this is also from NEET UG paper 2021. So central maxima, width of the central maxima, we know that we have been discussing this. Okay, so d lambda by a. So it depends on lambda, a and d. So distance between the slit and source, that we don't know. Wavelength of the light used and width of the slit. So these two, I think 2 and 3. Wavelength of the light and width of the slit, both are there in this. So option number 2 and 3. So this B option will be correct. All right. So guys, we will stop it here for today. We'll meet again in the next class, and in that class we'll take up numerical problems from diffraction pattern. So this diffraction of light from the previous year's JEE papers. Okay, JEE advanced and JEE mains. Okay, so thank you for your patience. Bye for today.